Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this clip we calculate percentage composition by mass of each element in an empirical formula and then go on to calculate an empirical formula using percentage composition values.
Okay, so we're going to look at percentage composition. It's a very important technique. If you make something in industry and you want to check what you've got, then the very first thing you'll do is you'll get an elemental analysis, and you'll use that elemental analysis to work out what the percentage composition of your material is, and that will lead you to your formula. Okay? So we're going to look at what percentage composition is and how it works with that. It's very simple. So let's take an example, and you've just done a test. Okay, so I've got 15 marks out of 60. What percentage have I got that's correct? 25%. How did you get that number? 15 divided by 60 times 100. And what you've actually done is you've just told me what your percentage composition of the test that you got right. So that's what that percentage means. Okay? So So this means so it's just telling you 25% of that test is the composition of what I got right. And so we can just extend that to a formula. Okay, so what we're going to look at is if we've got a formula, we're going to see what percentage of that formula is one of the particular elements in the formula. And then if we look at all of the elements, when we take their percentage compositions for each of the elements and add them together, we should get what? 100%, because that's what makes up the whole of the compound. And it's exactly analogous to this. So we can extend this to chemical formulae. Okay? Before we do that though, we need to see or formalise what exactly we've done here. Okay? So what we did was we took what I got right divided by the total mark times 100%. Yeah? So if we now look at a chemical formula, if I want to work out what the percentage of that formula is aluminium, how am I going to do it? What handy value can I use? Or, if I want to do it percentage by mass, so you use the molar mass, don't you, or the atomic mass. But I've got 2 of those. And I've got 3 of those, so I've got to allow for it. So the first thing I need to do is to work out the total mass of this, which is given by the molar mass. So molar mass of aluminium aluminium, we know, as we've seen before, we just take the sums of the atomic masses of each of the elements. So I'll just put it like that. So I hope you've got that. So aluminium, we go to our periodic table, which you will be given on the day. So 2 times aluminium, which is 2 times 27. Okay? 2 times 27.0 plus 3 times 16.0. Good idea to use brackets all the time, and then you won't make a mistake when you come to put this into your calculator. 54 plus 48 is 102 grams per mole. So that's our total mass. What we can do is work out what fraction of the mass is aluminium. And if we go to this part here, the part I got right is the fraction that's aluminium. The total marked bit becomes the total mass, which is the molar mass. Does that make sense? Yeah? So what I can do is I can adapt that formula from the part I got right is mass due to one of the elements divided by the total mass, in other words the molar mass, times 100. Okay? That's our percentage composition. And it's a percentage composition by mass, because we're doing everything in terms of masses. Yeah? What we're ultimately going to do is not look at a formula and work out what the percentage composition by mass is. We're going to go the reverse direction. We know we can do experiments where it's very easy to measure the percentage composition by mass of individual elements. When we've got those values, we're going to use them to work out the formula. Because that's what this is about. How do we ever get to know what a formula of something we've got? And it's using percentage composition data. So let's do that with this one here. So what we've got is 2 times aluminium. So percentage So if we're looking at the percentage composition of aluminium in aluminium oxide, it's 2 times the mass of aluminium divided by the molar mass of Al2O3. So 2 times aluminium, we've already got, is 2 times 27.0, and the molar mass of aluminium oxide, the total mass, is 102. And I multiply that by 100%. Could somebody quickly calculate that? It's 54 over 102. 52.94%. It's 52.94. So 9%. Okay? Now let's have a look at the percentage composition of O in Al2O3 is equal to 3 times the mass of oxygen, because there's 3 oxygens in it. Okay, 3 times 16 divided by the molar mass of Al2O3, which is equal to 48 divided by 102. If somebody else could calculate times 100 to make it into a percentage. You didn't even calculate that, did you? Yeah. So if you ever get one, you will get a question like this, and if you're asked to do all the elements, the thing you do at the end is add up all the percentages, and it should come to 100%. If it doesn't, then you've made a mistake somewhere. Okay? This is all well and good, but what we actually want to do is the opposite. Okay? We want to be able to take a percentage composition measurement, which we can get by experiment. And if we've got the percentage composition of each of the elements by mass of a substance, we can work back to exactly what the composition is in terms of its moles. In other words, we can work back to the formula. Okay? So before we do that, I want to quickly remind ourselves of what we mean by a formula, what that actual formula means, and the different types of formula, because there are 2 types. Okay? Let's start with empirical. And this type of formula can be applied to all types of substance, regardless of what particle we're dealing with. So it can be molecules, ions, or atoms. And this gives us the simplest ratio of each of the elements in a substance. So if we take a simple example like magnesium chloride, what this means, this is an empirical formula, okay, is telling you for each magnesium we've got 2 chlorines, or chlorides in this case, okay, or for every mole of magnesium we'll have 2 moles of chlorine, yeah, because we're just scaling it up, okay. So empirical formula can be used with any type of substance. In fact, it's the only formula you can apply to ionic substances. Okay? So if we look at this, okay, so that's what it means. The empirical formula, in the simplest interpretation, means for every one of those, we've got 2 of those. That's the ratio. But we now don't deal with individual ions or atoms. We're scaling it up to be something more meaningful. So in terms of that, it means for every 1 mole of magnesium, we've got 2 moles of chlorine. And that's what we're going to use, this ratio of moles that make up a formula. Okay? And coming back to Chris's comment before about what do we do about numbers in front, we don't have numbers in front. We're only dealing with an individual particle or a mole of those particles. We're not concerned with what they're doing in a reaction yet. Okay? What we really need to be able to do then is to go back from a percentage composition to a formula. Okay? Because we can get these measurements of percentage composition from a practical measurement. You don't have to do that, but there are fancy machines that do it now. And having got that, this is what they do in the real world, okay? Having got the analysis, the chemical analysis, which tells us the percentage composition, the first thing you can do is work out the empirical formula, and that's what we're going to spend the last 10 minutes doing. It's pretty straightforward. I'm going to do it with a very simple example. Okay? Then we'll look at a different type of formula, a molecular formula. How do we get that from an empirical formula if it's not the same? Okay? So we're going to start with something really simple. Always start simple. Okay? We've got an organic compound that's made up of C and H, a hydrocarbon. And there are millions of these, many of them. And we've got this substance, and we send it off for chemical analysis, and it comes back that 75% of it is carbon, and 25% of it is hydrogen. Okay, what's the formula of it? Because that's what we're going to try and find out. Now, what we've been looking at so far is looking at percentage composition by mass. That's just giving me a percentage. How can I make that into a percentage composition by mass? A very, very obvious thing I can do. I take 100 grams. So if I've got 100 grams of this substance, what mass is going to be carbon? 75 grams. What mass is going to be hydrogen? 25 grams. So that's my starting point. What I'm going to do now is then, once I've got that, I've got the mass of each element. What are these formula in terms of? What did we say they were in terms of? Moles. I've got a mass, but I need moles. How do I get moles from mass? L equals m over n. Okay, so little m over big M. Okay, so the first thing we need is to get a mass. So we assume 100 grams of substance. Yeah? Okay, so we've got C equals 75 grams, H equals 25 grams. Now we need to convert that to moles. And we've already looked at this. N equals little m over big M. So C, so I'm going to put N of C equals 75 divided by 12.0, if somebody could quickly calculate that. And the number of moles of hydrogen is equal to 25 divided by 1.0. Okay, so somebody could tell me what this is? 6 what? 6.25. Okay, and this one? 25. Yeah? Now, what that's in fact telling us is we've basically got the formula. It's telling us that what we've got, if I've got a green pen, I could finish here. And this is telling us our formula is C 6.25, H 25.0. Is that falling into my simplest ratio bracket? No. I don't. That's not a simple ratio. It's not the simplest ratio by a long way. How can I simplify that? Yeah. Easy, isn't it? You know it's simple, you've got the answer. But what you do is, I can turn this into a simple number by dividing it by 6.25. If I divide that number by 6.25, I need to divide that number by 2.25. So the first thing you need to do is get one of the elements, the smallest number, to 1. And to do that, you divide by the smallest number. If you do 1 by the smallest number, you've got to do everything. Okay, so divide by the smallest number. C, sorry. H is 25.0 divided by 6.25, which is equal to 4. How convenient. So in other words, our empirical formula is CH4. So that's methane.